So here's a definition of what it means for A to be congruent to B mod n. So if this is true, then as a result, all of these statements are also true. And all of these are pretty much saying the same thing in a different format. Now, you probably know what this is already, but just in case you don't, let me take 1 minute to explain what this is. If you know what this is, fast forward 1 minute. So here's just a random example. So let me think of a random number like the number 17. Now, let me take the number 17, and from it, let me take away a random amount. Let me take away 3. And let me do this as many times as I can until I run out of space. Okay, let me just keep going here. And I can do this one more time, and then I have to stop because I can no longer take away 3 because I don't want to go into negatives. I want to keep it positive. So here is what we say. Here, based on this observation, we say that 17 is congruent. That should be straight lines. 17 is congruent to 2 mod 3. So that's the original number. This is the number that you are subtracting by every single time. And this is the remainder after you're done doing all the subtractions possible. Now, just another FYI. Take the same 17 and divide it by 3. So this goes into that 5 times. That's 15. And this is 2. This is the original number, the dividend. This is the number that you are subtracting by every time, the divisor. This is the quotient. Here, the quotient 5 appears in the number of times that you were able to subtract 3. We were able to subtract 3 5 times. And after doing all that, the remainder 2 is what we got. So there are serious connections between these things. Now look, let me just compare. If this is true, which this is, then I can build this. Let me just build that based on this. So if that looks like this, so A is 17, B is 2, and N is 3, then this here, based on that, would say 3 divides A minus B, that minus that, this minus this. So I'm just following the pattern. Now this is true because that's 15. 3 divides. That vertical symbol means division in the sense that this number can split this number, and it can because 3 can split or divide 15. So that's true. I believe that. And then from here to here, I say, okay, then this number here equals that number 3 times some number k, which is some integer. And that's true because 15 equals 3 times some number 5, which happens to be the quotient, which is the number of times that I was able to remove this number from that. And to go from here to here, they just added b to this side. So that's how this is just a quick rundown of how this works. So now here's the actual problem at hand. This is what we have. This is given to us for free. This is what we're trying to prove. So let's assume that this is true. We have to show that this is also true as a result. Okay, so what do we have? We have that this is true. Well, if this is true based on this definition, then all of these are also true. So let me build this one. Let me go from here to here to here. Then based on the definition here, we know that n divides this difference. And if n divides this difference, then that means that a minus b is equal to n times some k, where of course k is an integer. Now I want to do something a little different, but let me add the b to this side actually. So a would be equal to nk plus b. Now what I want to do is this. I want to actually protect both sides, and I want to square both sides. So a squared, and then this squared, I just write it down twice. And now why don't we actually perform this expansion? That should be it. When you carefully expand that binomial product, it should be this here. Now let me just move the b squared to this side. Move that there, boom, boom. Now I notice that this is what I'm left with, but you know what I see? I see that I can take out an n and a k as a common factor, as the greatest common factor from these two terms. So I have a squared minus b squared equals this times this times this. Let me write this again, but let me put some dots in between. Look at what we have. This is equal to this number times this number times this number. These are 3 numbers. and all together when multiplied, they give you this back. And based on that, let me just give you another quick demonstration here. Consider the number 30. 30 equals 2 times 3 times 5. 2 times 3 times 5 is 30. So because this times this is this equals that, you know what that means? That means that 2 individually can divide into 30. That means that 3 individually can divide 30. That means that 5 individually can divide 30. If blah, blah, blah times blah, blah, blah times blah, blah, blah equals that, then each of these components can individually divide that number. And that's the same thing here. This times this times this is that. So this can divide that, this can divide this, and this can divide that. But I'm not going to write all 3 statements. I'm only going to write down the one that I actually need. And the one that I need is actually the one that's n. So because this times this times this is that, that means that this n can divide a squared minus b squared. So what I want you to see is that this here looks just like this. It has the same structure. It's slightly different, but that doesn't matter. What matters is it has the same format. So I'm going to go from here to here, but using these values. So placing things in the correct spot, here is what we should get. We should get a squared, that's there. This guy went there, so this guy goes here. And then congruent. And up next, I should write whatever this object is, which for me is going to be b squared. And up next, I should have some parentheses. And inside the parentheses should be mod whatever this is. And that happens to be the same n. And if you look at what we were trying to show, perfect match. See that? So there should be some words in this proof, like you should add some English to this to make it a little smoother, but that's the general gist of it. Now let me just say this for part P, the one where you have to show that n cubed minus n is congruent to 0 mod 3. By the way, that happens to be true, but here's the thing. The proof of this, I've seen this before, but it requires proof by induction, where you have like a base case, then you have like the induction step, and it's a very technical proof. So if you guys have actually done proof by induction, let me know and I'll work this out, because that's the only way that I know how to do this properly. But if you guys have done it a different way, let me know. I will say this though, n cubed minus n, that's the same as this here. If you factor out an n, and that's the same as this here. And what I want you to see is that these are 3 consecutive numbers. N minus 1, n plus 1. These are 3 consecutive numbers. And if you add these 3 numbers together, you're going to get 3n, which is a multiple of 3. So there are some serious connections between the factorization of this and the sum of the numbers that you get back. But again, I'm not too sure what you guys have done. Let me know what's up with P if you want, and we'll go from there.